Hey guys, so this is the review video for intermolecular forces. In particular, I'm going to go over the Phet lab and what you need to know for it. So our first question is, what is an intermolecular force? So I want to draw our attention to, I did this in class with us, but we went over prefixes. So we have been talking about intramolecular forces. So intra is prefix, which means within or inside something. So an intramolecular force just means the bond between different atoms. So for example, if I have an ionic bond between sodium and chlorine, then that intramolecular force is that ionic bond between sodium and chlorine. So this Phet lab goes over not intramolecular forces, not bonding, but intermolecular forces, which means between two groups. So an intermolecular force is how strong an attractive force is between individual atoms or molecules specifically. So for example, if we look here, this is hydrochloric acid. It's hydrogen plus a chlorine. And we can see these hydrogen and chlorine, they're represented here with a circle, and there is a covalent bond between them. That is this line drawn. And covalent bonds are very strong. So that's the intramolecular force, is that covalent bond. Now the intermolecular force just means that chlorine kind of hogs this electron away from hydrogen. And because of that, both hydrogen and chlorine, hydrogen ends up a little positive, chlorine ends up a little negative. And so if you get more than one hydrochloric acid molecule together, then there's a weak attraction between this chlorine and this hydrogen. Not enough to bond them together. They're not bonded. Now, they're just sort of attracted to each other based upon their differences in charge. So with that, let's take a look at the formative. So this was the formative that you're on. I'm going to be previewing as a student over here, just so this is what you should see, but kind of bigger. And actually, let's make this bigger. There we go. Okay, so there was a Khan Academy video, and then I also posted this video, which is pretty good. Both of them go over in pretty good detail about what intermolecular forces are and the different types. Now, we don't actually have to know the different types for our class. That's something that's covered more in chemistry, and then again in AP chemistry. But it is important just to know how intermolecular forces affect things together. So let's go over a couple of these. This is, of course, a thermometer. And in that thermometer, there's a C or a K. Now, here in the US, we're a little bit more familiar with the F, that stands for Fahrenheit. And the C or the K, the C stands for Celsius, which is more commonly used in other countries. And then Kelvin is a temperature a way of measuring temperature that's more common for scientists to use because it measures big temperature extremes, either the really, really cold or the really, really hot. So if I was referring to maybe the temperature of the sun, I would use something like Kelvin. Okay, these are the different states of matter. So we know, of course, that they're gas, liquid, and solid that the simulation shows. And then we're going to go through some of these things together. So first of all, let's look at our atoms and molecules. And actually, let me pull up a periodic table real quick. I really like using p-table because it's really cool. Okay, so we have neon, argon, oxygen, and then water, which is the only molecule. So neon, argon, and oxygen are all elements. They're all kind of neon and argon are by themselves. Oxygen here is composed of O2. So this is oxygen as we usually have it. It's an oxygen molecule bonded to another oxygen atom. And then water is, of course, H2O. Okay, so let's look at what neon and argon are. So here's neon here, and here is argon. And they're both in this 8th column, which means that they are a noble gas. And because they are a noble gas, what is the thing, guys, we know about noble gases? They are really non-reactive. They have a full outer shell. They don't need to interact with anything. They do not form bonds with each other. They do not form bonds really with most anything except for under extreme conditions. So then we also have oxygen, which again, it's an oxygen bonded to another oxygen. So this does have a covalent bond between it. So let's look up O2. If I look up the images, let's see, let's do the covalent bond diagram. Okay, then yeah, perfect. Here is one oxygen and another oxygen. This is the Bohr model, and it's just showing how they're sharing these two pairs of electrons. So it's the same atom, but it is in a covalent bond together. And then finally, we have water, which, as I might remind us, water hydrogen bonds. And this is kind of, let's see, where's a good picture for this? This one's really good. I like this one. Okay, so there is a covalent bond between the oxygen and hydrogens, true, but something else is happening. That oxygen hogs those electrons, again, away from hydrogen. It's kind of a bully about it. And because of that, oxygen's a little bit negative, hydrogen's a little bit positive. So based upon what we know about how negatives and positives attract each other, then if I have more than one water molecule together, it forms this weak hydrogen bond between them. Now, this hydrogen bond, it's not super strong, but it's just strong enough to give water all of its cool properties. So water forms hydrogen bonds. And so if we look up something, a quality we know, like surface tension, here is a water strider that's walking across the water. Here is a, oh, this one's kind of cool. It's a US swimmer, and you can see this layer of water around them. This one's another, they kind of look like a little creepy there. And then you guys saw how many paper clips I was able to fit on some water. And if we look at something else, even like just cohesion between water molecules, if we look at how these water droplets look on this blade of grass, all of those things, these are water molecules sticking together, and they are sticking together for the same reason. They're sticking together because of hydrogen bonds. So that is your little intro right there. So I'm going to demonstrate a little bit. If I make these a liquid, actually, let's back up for a second. So this particular this particular Phet lab is about melting and boiling points. A melting point is the temperature at which a solid melts into a liquid. So water, we're talking about when it goes from ice to liquid. And then the other one we're looking at is boiling point. Boiling point is when something transitions from a liquid into a gas. So for water, it's the point at which it starts to boil. Maybe you can boil it in a pot, and then it turns into water vapor, which is a gas. So we're looking at when these things transition either from a liquid to a gas, the boiling point, or a solid to a liquid, the melting point. So right now I'm going to look at boiling point real quick. We're going to look at the boiling point of these different atoms and molecules, okay? So if we look at water here, we see that it's all a liquid, and then I have to raise the heat. So I'm going to put this on Celsius just because it's a little easier for me to work with. I'm going to raise the heat. So we're about at 60 to 70 degrees Fahrenheit, moving on up there to about 100. And the water molecules are starting to float away a little bit. So I have to raise the heat a little bit more. There we go. There's a lot more energy. So that's something else we haven't talked about too much yet, but the idea that heat and energy are kind of the same thing. Heat is a type of energy, thermal energy. And, there we go. Okay, so we see this water molecule going crazy, right? So this is water going from a liquid, again, mostly down here, to floating around. It's got a lot more energy. It's spinning very erratically. And so now it is largely a gas, starting to settle though. Okay, so we had to put some heat though into that, right? All right, so I'm gonna reset it. So we're back to, oops, nope. Okay, so now we are back to this temperature. So if you'll notice up here, it is showing us the temperature at which neon is a liquid. So right here, neon is a liquid at negative 246 degrees Celsius. Whoa. Let's compare that to what water was again. 13? 13 compared to negative 246 degrees Celsius? That's crazy. So now if we want to make neon from a liquid to a gas, I'm going to have to just barely heat it up just a little bit, and boom, it starts to do that at negative 217 degrees Celsius. So it does not take very much energy. Argon, same thing. Argon, negative 187 degrees Celsius. That's when it is a liquid. And if I want to change it to a gas, then I do not have to change the temperature very much. So we're still in the negatives. So think about when water is frozen, these things are gases already. Now let's look at oxygen. Oxygen is a liquid at negative 216 degrees Celsius, becomes a gas at negative 160. So again, we're still in the negatives. So our question is, water becomes a solid, negative 127 degrees Celsius. That's not quite true. That's when it's originally a solid, but it freezes below that. Here it's showing it as a liquid, and then here again is a gas. So our question is really, why does it take so much energy to change water from a liquid to a gas? What is it about water that I have to put in more energy or more heat? I have to heat it up more to change it from a liquid to a gas and from a solid to a liquid. Well, the reason for that is because each of these hydrogens and each of these oxygens is also barely connected to each other through hydrogen bonding. Hydrogen bonding, by the way, is a intermolecular force. So if we look at this again one more time, then a intermolecular force, this is actually a pretty good drawing of it. So this little squiggly here, it looks like an 8 that someone didn't complete, just means partially. It means that oxygen's kind of negative because it's just sort of hogging that electron, but it didn't steal it away like an ionic bond, so it's not fully negative. So partially negative, partially positive. So let's go through some of these questions. All right, how are they different? This is just describing what molecules look like when they're liquids, gases, and solids. So describe them in terms of how closely connected are they and what does their movement look like? Which one engages in hydrogen bonding? The only one that has hydrogen in it, which is water. Argon, not hydrogen. Oxygen, not hydrogen. Neon, not hydrogen. All right, lowest melting and boiling points. So this is looking at which atom or molecule requires the lowest temperature, the lowest amount of energy to either melt or boil. It's going to be one of the noble gases. And then highest one, we looked at that already, and that is water. So why do you think it takes so much energy to change water? Because there are hydrogen bonds between water molecules. That is our sample response. Okay, so let's look at a couple other things. So let's look at a few hypothetical molecules. We have ammonia and we have methane. So let's talk about polar versus nonpolar. I kind of look at this for a second. So an ionic bond, super strong. Actually, let's do... Okay, perfect. Gotta love Google. Okay, so polar molecules. Polar means that the bonds are not shared very well. So the electrons in polar molecules are not shared equally between them. Remember, polar and nonpolar are just different types of covalent bonds. Polar, they're not shared equally. Nonpolar, they are shared equally. So because these guys are shared equally, there is a... Hold on for just a second. It was a bad example. Let's see. I should have found this already. Did you? I guess that could kind of work. Well, we'll just go back to it. Okay, so because a polar molecule is not shared equally, typically speaking, on polar molecules, there's going to be some kind of partially negative charge and a partially positive. And then methane, when things are non-polar, they're being shared equally, it means that everything's sort of equally balanced. So one of them is going to have a higher amount of energy. It's going to take more energy to transition it between stages because it's going to form bonds between things. All right, now this one. This one confused some people. So we're going to go to this Phet lab, 3 atoms specifically. You'll notice that it looks like, does it look like water maybe? It does. So we're going to select bond dipoles and partial charges. And then do we turn the electric field? Okay, so we leave the electric field off. Again, squiggly sign, Greek letter delta. There's a partial electric charge. All right, so we are looking at, So first we go through and we basically say, this looks a lot like that oxygen, and this looks a little bit like hydrogens, and I would notice that this is more negative, and these are kind of positive, okay? So then if I had something else that had a negative and positive charge, like sodium, I have sodium, one of them's positive, one of them's more negative because they're moving those things, and I put it in a bunch of water molecules like this. Which side is sodium, which is more positive, going to be attracted to? Is it the oxygen that's slightly negative or the hydrogen that's more positive? So then I can go down to the 2 atoms one. So we're going to click back to 2 atoms. Let's see. It's really hard to click right here. Let's hide that. 2 atoms. And here we go. So now let's put the partial charges on, and I believe that is it. Yeah, none. Okay. And there we go. Okay. So now the electronegativity is in the middle for both. These 2 things are clicked, so we are good there. Are there any charges on these 2 things? What do you guys think? All right, so if this molecule found one just like it, so there was an A and B here, and there was another A and B, do you think that they would be attracted to each other? Why or why not? Are there any partial charges? Explain why the atoms now have partial charges. Oh, let's go. Okay. So then let's look at this was a slightly different molecule. So this may be, before it looked a little bit like an oxygen bonded with another oxygen, and maybe let's say that this looks a little bit more like our HCl example from earlier. So now they have partial charges because we increased our electronegativity. So in this particular one, if this molecule found one just like it, and one side was more positive and one side was more negative, do you think those molecules would want to be together, or do you think they would want to be apart? All right. So in terms of greater melting and boiling point, the oxygen-like one that you made, so again, that is the oxygen-like one that they're talking about, that is this guy with no partial charges. It is just neutral and neutral. Do you think that that one would want to form bonds in the same way that this guy does, this one that's more like water? So if you think back to this Phet lab, oxygen versus water, which one of those required more heat, more energy to change from a solid to a liquid and a liquid to a gas? So here, this is a CER, claim, evidence, reasoning. Your claim is just, I think, that either one of these would require more, would have a greater melting and boiling point than the other. So you get to pick either the oxygen-like one or the new one. And then your evidence, so this is just stating your evidence. So you might say something like, oh, in this particular Phet lab, the temperature was only blah, blah, blah for this versus this one. Or you might say, hey, in this Phet lab, the charges on these molecules were blah, blah, blah. And so I think this would happen. And then your reasoning. So you can include here information about hydrogen bonds, about what intermolecular forces are, about what sodium chloride here would actually be attracted to, and so on and so forth. Really just any reasoning that you have to support your response. All right, guys, this is it. This Phet Lab is for a grade. Sorry for the very long video, but I'm hoping that it helps you out.